Okay, so good morning, everyone. Welcome to this seventh lecture on quantum simulations with atoms and photons. The topic that I would like to discuss today is superradiance. And first of all, I would like to spend a few moments about distinguishing two different types of superradiance. So it turns out that this term, superradiance, is used in two different contexts that are actually quite different one from each other. There are some analogies, but eventually they're like two different effects. So that's quite misleading, that there are two physical effects that actually are quite different, and they are termed by the same name, superradiance. So let me first discuss the first type. I'm going to spend more time on the second type, but let me at least qualitatively discuss the first type, which was actually the first time that this term was used. So it was introduced by a researcher named Dicke, and Dicke discussed the following problem. He assumed that he wanted to discuss, say, a two-level system that is decaying in free space. So this is the normal case of spontaneous emission. And then he asked the following question: what happens if we put many atoms? So let's assume a situation in which we have many atoms in free space, and they are allowed to spontaneously emit light. Okay, so it's quite important. This is in free space. As we will see, the other type of superradiance is actually in a cavity. So that's one way to distinguish between the two phenomena. So naively, one would say, okay, let's assume that if we have, say, one atom. So let's term n the number of atoms. So if n is not, 1, so then the intensity of light, I, as a function of time, t, will basically decay as a Poisson, right? There is this exponential decay in terms of the intensity related, if you want, to the probability of having a spontaneous emission event. Now, if you put in n atoms, naively one would say, well, you should have the same phenomena, just multiply by n times. So if you have n independent atoms that spontaneously emit, what you will see is say, the same phenomena. So the time scale is going to be the same, but of course the intensity will be much higher. So something like this. Okay, so let's say the intensity is going to be proportional to n, but the time scale is the same. So if this time scale was kappa, then we have the same time scale, kappa. Okay, this would be the case of uncorrelated spontaneous emission from n atoms. Right, it's quite trivial. Now, what happens if instead these atoms are one on top of each other? So when they are one on top of each other, basically there is a feedback, in the sense that when the first atom emits a photon, this photon can cause the stimulated emission of the other atom. So one now needs to consider the coherent emission of all these ensemble of atoms. Okay, so the first case was, say, uncorrelated spontaneous emission. This is what one would call, say, the normal case. What is the superradiant case? Superradiance. So in the superradiance case, what happens is that now if I plot the same plot as a function of time, what I will see is that now the time scale will be much faster. And again, this is related to the fact that this is now a collective phenomenon. So one way to think about it is sort of this stimulated emission, one from each other, from one from the other. But you can actually, the treatment by Dicke was really a quantum mechanical treatment using tools that we will mention later on, using what is known as the Dicke manifold. So he really gave a quantum mechanical treatment of the problem. What he observed was that actually now the decay is much faster. So the decay, instead of being on a time scale, so this is time and this is the intensity of light, and so the time scale is now going to be kappa over n. So the decay will be much faster. It's not that each atom is emitting light independently, but they are all emitting coherently. And as a consequence, now the total energy is conserved. So if before we had an intensity that went like n, now we will have an intensity that goes like n squared, right? The total amount of energy that is emitted is the same because we have all these atoms that go from the excited state to the ground state. It's just that this effect happens much faster. So the intensity of light is much larger, is n squared, and the decay time is 1/n. Okay, so this is known as Dicke superradiance, and it was introduced by Dicke itself. Okay, question? No. Okay, good. So this is, say, type 1. Now, type 2 is something that is actually goes under the name of Dicke model. And if you want, the Dicke model actually was not introduced by Dicke himself. It was introduced probably first by Hepp and Lieb. And if you want to learn about this model, so some basic things I will teach today. If you're interested in more references, you can look on a Wikipedia page, Dicke model. So if you go to Dicke model, you will learn more. I'm mentioning this page because actually More and myself sort of created this page and realized the first version of the page. So I think it is quite, it's good. Okay, that's, I mean, I did it. So yes.
Question on the first type. You say that the atoms have to be, two-level systems have to be one on top of each other. Can you kind of quantify the distance between them?
Excellent question. Yes, very good. So essentially what you need is that the decay of all the atoms is in phase. So in other words, what you need is that the distance between the atoms is within a wavelength of the light. So much smaller, okay, this is a good question. So the distance between the atom, distance should be much smaller than lambda, which is the wavelength of the light, and then all the atoms can emit coherently. So that the emission from all the atoms is sort of in a constructive interference. Okay, that's basically the condition. Now, in principle, you could also, if you also spaced all the atoms by lambda, that would also be fine. So if you can place all the atoms at exactly different distance lambda, then this also can lead to superradiance. But in general, this is not the case. In general, if you just have a gas of atoms and they are spread over a large space, then the distance will be sometimes lambda over 2. So constructive and destructive interference sort of average out, and you end up with the uncorrelated spontaneous emission. Actually, let me drag this condition down. So this is what happens in the case of superradiance. If instead the distance is, say, much larger than lambda, then you have just the normal, just uncorrelated decay events.
So, I mean, constructive interference happens when there's a certain integer, right? The distance is the integer multiple. So,
well, it could be also, if they are also, say, at the same place, if the distance is much smaller than lambda, then you can think.
Oh, so it looks like one single emitter, basically. So when you're far away, you're saying that when you're far away, the million emitters look like a single emitter.
Exactly.
Because they're
it's not, I mean, actually also when, because the question is, do they feel the same field? This is really the question. You need them to be, to couple to this electric field at the same place, the same electric field.
Right. Okay. So the addition of the phase is essentially one. So, okay, I understand. Yeah.
Right. Actually, what I said before about the fact that they can be displaced by lambda, that's actually not correct. It will be correct for the second case, as we mentioned. In this case, in the case of Dicke superradiance, doesn't work because we are in free space, so light can be emitted in all directions. And so that's why you cannot, I mean, for some photons, it will be fine. Let's say that I place two atoms at distance lambda. So for the photons that go in this direction, that's fine, but in the other directions, it doesn't work. So actually, no, you really need all the atoms to be placed within lambda distance. Okay, So what is the Dicke model? So the Dicke model is essentially sort of has the same flavor. That's why the same name was used. And there are also some similarities, but also important differences, which I will mention. And the Dicke model is actually a model of n two-level systems that are placed inside a cavity. Okay, so that's the key difference. The Dicke model is in a cavity. So you have a single mode cavity. In other words, the model that you would like to write is, say, some Cummings model. So it would be something like omega 0 Heidegger A, so a single cavity mode plus many spins. So for simplicity, let's assume that they are they're all the same two-level system. It doesn't need to be the case, but for simplicity, so you have an index I that goes between 1 and n. So this counts the number of atoms, and they are all two-level systems. So I describe them in terms of Pauli metrics. And there is a coupling, and the coupling is something like this. So it could be sum over I, A plus A dagger times sigma plus I plus sigma minus I. This is based, okay, that's with a prefactor G. Okay, this is essentially what is written here is essentially sigma xi. So there is a single cavity coupled to many two-level systems. Okay, and that's the difference in the case. The first case, the Dicke superradiance, it was in free space, while the Dicke model is in a cavity. So you have a single cavity, and then here, in principle, you can use this argument that I was telling you before. So the atoms can be either all in the same place, or say displaced by exactly one wavelength. I will mention more details about the experimental realization as time goes on. Okay, so what did Heppenlieb do? Heppenlieb did what is known as the rotating wave approximation, RWA, rotating wave approximation. It later turned on that this approximation was actually not really needed. I mean, you can solve the model in the large n limit even without the rotating wave approximation, and that's something you are going to do in the homework. But for simplicity, let's consider the case of doing a rotating approximation, which means that we neglect terms that are like A sigma, say A dagger sigma plus. So something that in which both a photon is created in the cavity and the two-level goes up. So this is sort of the counter-rotating terms. These are counter-rotating terms in which you both, the energy is essentially not conserved. You both create a photon and move your spin from up to down. So you neglect those terms. And then, okay, one can ask, is it justified or not? So, but for the moment, that's what you do based on basically energy conservation. And then what you are left with is a model that is known as the Cummings model. Cummings model, which is the same model as before, as the Dicke model, but without the counter-rotating term. So for complete, let me write it down. TC, Cummings, it's omega 0 Heidegger A plus sum over I sigma Z, so omega Z sigma Z I plus sum over I G Heidegger sigma minus plus A sigma plus. Okay, sigma I, because you have many atoms. Okay, so what you can do in order to analyze this model is now to define a collective spin operator. Okay, so what are the collective spin operators? It would be, we usually denote them as large S. So sigma would be a Pauli matrix, and large S, it's going to be a large spin. Actually, let me actually assume that the sigma are not Pauli matrices, but the spin half operators. Spin half operators. So you know that the difference is that there is a 1/2, right? The Pauli matrix, you know that it's +1 or -1. The spin half operator is +1/2 -1/2. So it's basically just the Pauli matrix divided by 2. But in all these cores, factors of 2 don't really matter. So it's going to be the same. But to make a statement precise, to make the definition of the total spin precise, we would like to use these spin half operators, which are half of the Pauli matrix. So then we define the spin, let's say total spin X which is going to be just the sum over sigma ix. Okay, just the total spin. And in the same way, there is going to be a total sy, a large sy, a large sz. There is also a large s squared. So the sort of the total spin, the size of the total spin, which is going to be sx squared, sy plus sy squared plus sz squared. Okay, let's put parentheses. This is the total spin squared. And first of all, what one notices is that these operators satisfy the normal spin commutation relation. So for instance, you can see that, say, Sx, Sy equals to I, Sz. So they really behave as spin operators. Okay, they have the usual spin algebra. And also, for the same reason, you can also see that S squared commutes with Sz. So that means that you can build the basis of states that is both eigenstate of the total S squared and Sz. Okay, so you have just the usual spin algebra that you have the total spin and the Z component of the spin. Okay, so this is not so you can build an eigenbasis using, say, S squared and Sz, some state that have a well-defined S squared and a well-defined Sz. Incidentally, this notation in the quantum optics community is called the Dicke manifold. Dicke manifold. So, and the reason it's called in this way is that basically Dicke he didn't use it, the notation. If you go and read the paper of Dicke, the original paper of Dicke on the superradiance, the language is sort of not the same. It's a little bit different than the one we use now. So the notations are a little bit different, but eventually it's the same physics. So the way that Dicke described this collective decay of n atoms was moving to this total spin frame. So essentially, what he noticed is that this is equivalent to coupling, to having, instead of having a two-level system that decays, you essentially have like a large dipole that decays. And this is why the effect is much faster, because the effective coupling between the large dipole and the vacuum, which is the spontaneous emission, is much faster. Okay, so that was Dicke model. And again, I don't want to go into the details, but I just want to mention that in the quantum optics community, you may find these words, Dicke manifold. It's important to know what they are talking about. It's just the total spin. It's the total spin. Okay, good. So now what we obtain is, so we can rewrite why we can introduce these spin operators, because as you can see here, what really comes up is just the sum of all the spins. Okay, so you see that what you really have is assuming that all the omega z are the same. So that's a key assumption here to obtain this simplification. And also here you see that there is a sum over I sigma minus I with single plus I. So in other words, you don't have you don't have the single spin. Always the sigma operators always come as a sum of them. You always have a sum of them. So you can rewrite the Hamiltonian in terms of omega 0 A Dagger A plus omega z S z plus G times S plus A plus S minus A Dagger. Okay, so essentially this is really, if you remember our first lecture about lasing, this is really the James-Cummings model. I mean, it's exactly the James-Cummings model. It's just that instead of having a two-level system, you have a large spin. And if you want, you can solve this. You can solve the equation of motion. You can follow exactly the same procedure that we have used in the first lecture, and you can see first lecture. What you do, you can compute the evolution, the time evolution of A, and you can compute the time evolution of sigma z, the Heisenberg time evolution, of sigma minus. And what you see is that actually these can be written as, so you can have basically the one, it depends on the other, and what you see is that they can be written as some matrix times again A sigma minus, what you have here is I omega 0, I omega z, and here you have G times SZ, and here you have G. Okay, So again, this G sigma Z, I remind you, comes because when you compute the commutation relation between basically the Hamiltonian, so let me see, actually, no, actually this should be, sorry, the sigma Z should be here. Right. When you compute the time evolution of the sigma minus operator, then you need to commute the Hamiltonian with sigma minus, and then you have a sigma plus sigma minus, which is sigma Z. Actually, S minus S plus, which gives you sigma Z. Okay. And then I remind you from the last lecture, what we have seen is that if you are interested, so let's, like in the first lecture, let's consider the case on resonance. And what you find, so that omega Z equals to omega Z. So in this case, this is just a unity operator. So it's very easy to diagonalize. You don't need to do nothing. And what you obtain is that the eigenvalues are going to be, so lambda is going to be omega Z, I omega Z, plus minus square root of G squared SZ. These are the eigenvalues. You can see, I mean, it's quite simple to diagnose this matrix in the case of resonance. And so what you see, and that's now important, what you see is that, first of all, the system is unstable, like the laser. I mean, is unstable as soon as Z is positive. Okay, so if there is population inversion, if there is population inversion, meaning that the spins are mostly polarized up, then the system is unstable and it decays, right, by emitting photons into the cavity. So this is just the lasing instability. And yeah, so, and one point that I would like to mention is what is the maximal value of SZ? So I recall that SZ basically was defined as the sum over sigma Zi. So in the maximal case, the maximal value of this operator is n over 2, actually. So this goes from 1 to n. And so if all the atoms were initially polarized up, right, this is the maximal polarization, then what you obtain, this is, say, smaller than n over 2. So the maximal value for SZ is n over 2. When all the atoms are polarized up, this leads to the maximal instability. And you see that the decay rate of this instability, okay, decay rate. So the decay rate is square root of G squared sigma Z. So in other words, it's smaller than G times the square root of n, maybe over 2. Okay, so it means that we observe a phenomenon that is similar to the one that we saw in free space, and a little bit like in free space. Also in this case, the decay rate is much faster, but the scaling is different. In that case, the decay rate was n, went like n. When this case, it's only square root of n over 2. The reason is that we are discussing actually two different situations. In the previous case, we were discussing really the full decay. This was a decay process in which all the spins went from up to down. Here instead, what we see is only the initial instability. So there is not really, it's not really, yeah, okay, I'm now making a statement which I don't want to, I cannot really explain in depth, but this is related to the fact that the Dicke superradiance in free space is sort of a second order process. So it goes like G squared times n. While here, this is basically just a first order process between the spin and the cavity. So, I mean, the scaling is not exactly the same. Okay, so that's sort of simple. But this is not actually the question that Heppenlieb asked. Heppenlieb asked a slightly different question, which was, so I have given you an Hamiltonian. And what I told you is that this Hamiltonian is unstable. There is a dynamical instability of this Hamiltonian, provided that the atoms was initially prepared in the excited state. However, Heppenlieb asked a different question, and the question was, let's assume that the system is in the ground state. If the system is in the ground state, then what is the ground state of this Hamiltonian? Okay, so that's the question of Heppenlieb was really about the ground state. of H Davis Cummings. So we understand that if you prepare the state in an inverse state, so if you invert the spins, you prepare the spins in the excited state, then fine, there is an instability. But the question was, what about the ground state of this Hamiltonian? And for instance, you understand that if G equals to 0, there is no coupling. So what is the ground state of the Hamiltonian? So psi ground state would be a state just with no photons in the cavity. And well, sigma z equals to minus n over 2, where all the spins point down. But now what you understand is that when you turn on G for a finite G, there will be, you can use perturbation theory. So think of this term as sort of a perturbative term. So to first order, it does nothing because you would need to basically either, so initially you have no photons and all the spins are down. So there is no, if you apply G to first order, nothing, you cannot, this term doesn't lead you anything because you need to destroy photons, there are no photons. This term needs to pull down spins, but all the spins are already down. So first order is nothing, but to second order, you can have corrections. So to second order, you can apply G 2 times, and then you can say use the first term to create a photon and the second term to destroy it. Okay, so you can you will have some, okay, so let's say if G is small, you can use perturbation theory. And you know that in perturbation theory, you have something like, say, second order perturbation theory will be something like G square, psi ground state, and then here you have the perturbation, psi square, where the perturbation is this A S plus A Dicke S minus. Okay, these are typical terms that come into perturbation theory, and so they can lead to some finite contributions, right? You can have, for instance, in this term, you could have so B squared equals to many terms, but one of the terms is say A sigma plus, A Dicke sigma minus. Actually, let me consider the other one. Like this, right? And so this term, what this term can do for you, it can first let me see.
Creates and destroys a photon.
Sorry, you need to, sorry. Well, actually, in this case, even in perturbation theory, you wouldn't obtain anything because again, when you apply V on the ground state, you cannot create any excitation. So in this case, even perturbation theory wouldn't lead to any effect. It would, however, in the case of the Dicke model. If you had the Dicke model, in the Dicke model there are also these counter-rotating terms, and the counter-rotating terms can lead to where are the counter-rotating terms? Okay, this term here. There are some counter-rotating terms that can lead to an excitation. Okay, so in perturbation theory, nothing happens. However, if you plug in a finite G, okay, if G is large enough, what you can have a phase transition. What does it mean as phase transition? So think of the following. So as we mentioned, what is the ground state? So the ground state is that there are no photons and all the spins are pointing down. What are the two excited states? So in the excited state are basically either that you have one photon and say all the spins are in the minus direction, or there are no photons, but the spin points in the minus direction plus one. So you excite a little bit the largest spin. Okay. Now, what does this term do? This coupling term. So the coupling term actually basically can couple these two excitations, right? the V operator, what does for you, it can couple these two states, right? It can bring from the situation in which you have one photon, it can lead it to a situation where there are no photons, but you excited the spin. Agree? Yes, no?
Yes. Yes.
Yes, good. So when you have such a situation, you know that what you need to do is basically to diagonalize these. So there is this simple manifold of two states that is coupled by V, and you need now to diagonalize it together. So what you will have is that two new eigenstates are basically splitted, right? You have this phenomenon whenever you couple two levels that are at the same energy, any coupling will shift. You will create basically the new eigenstate with the superposition of the two states, one with a plus and one with a minus, and then we have either a little bit higher energy or a little bit lower energy. So what will happen is that the ground state happens nothing to it. Okay, that's what we discussed before, that the ground state is unaffected by the excitation, but these two levels are now splitted. Okay, let's assume here I'm analyzing the case of omega z equals to omega z. So I'm on resonance. So that initially these two states were exactly the same energy. Due to the coupling, what happens is that you now have a splitting, and the splitting goes as G. Okay, so this is basically omega 0. This was the initial energy splitting. This is the splitting between the ground state and the two excited states, and G is the splitting between these two states. And so what is the phase transition? What is the nature of the phase transition? The nature of the phase transition, and the phase transition will occur when this G is large enough. So essentially when G becomes larger than omega 0, if the coupling is larger than omega 0, then what used to be the ground state, what used to be the excited state will become a ground state. Because as you increase G, this level goes down and down, right? With increasing G, this level goes down and this level goes up. At some point, the lower excited state will cross and will become an even lower energy than the original ground state, which will mean now that the ground state is not only, is actually not the unoccupied state, but is a state with one photon. Actually, you can repeat the same argument for all the other excited states. So, this was the first excited state, but there is also a second excited state, in which you have, say, two photon excitation and or two spin excitations. And actually, at the phase transition, all those states cross. So, there are many excited manifolds, and each of these manifolds split, and there is a position in which all the excited states cross and become basically the new ground state. Okay, so it's really a phase transition. If you ask yourself what is the new ground state, you will see that the new ground state is actually a ground state that is extremely highly excited. Okay, so when G, let's say that when G equals to omega 0, then you have a huge, let's call it a huge level crossing. And this is what people would know as a quantum phase transition. In general, quantum phase transition means that you had an excited state that goes below a ground state. Okay, there is a level crossing. There is a gap that closes. Okay, you see, initially I had an excitation gap. There was an energy gap between the ground state and the first excited state, and this energy gap closes. Okay, and that's what we call a quantum phase transition. It's called quantum, first of all, because it comes because of quantum mechanics, and it happens even at zero energy. I mean, the ground state of the new system is different, is qualitatively different than the ground state before the transition. Okay, and this is this is basically known as the Heppenlieb phase transition, quantum phase transition. QPT. It's the simplest example of phase transition. It's mean field in a sense that there are only 2 degrees of freedom. There is no space. There are no dimensions here. So if you want a 0-dimensional problem, and it's the simplest example of a quantum phase transition. Okay. Questions? Okay, so let me now show you. So I have shown you this in a qualitative manner. Now let me show you how to derive the happen-leave transition in a quantitative manner. And the approach that I'm going to use can be also generalized to reintroduce the counter-rotating terms. So this schematic picture that I've shown you here is valid only in the case when there is a conserved quantity, which is the total number of excitations. So if you either have 0 excitations or 1 excitations or 2 excitations, and this problem is very simple. When you have counter-rotating terms, then it becomes more complicated. So you cannot solve it exactly as I've shown you here. However, you can still use this large N approximation that I'm going to present here. Large N approximation. Okay, so what I want to do now is to derive the large N approximation of the H Davis Cummings, okay, in the ground state. That's what I want to do now. So I'm going to use, we have this Hamiltonian, this H Davis Cummings, this Hamiltonian here, and I want to solve it using a large N approximation. And the same approximation can be also used with the full Dicke model with counter-rotating terms. So what is the idea? The idea of this large N approximation is based on something called the Holstein-Primakov approximation. Actually, Holstein-Primakov transformation, but let's call it approximation. I will explain. So let me explain you in words first what was the problem. The problem is that what we know to solve is harmonic oscillators. Okay, the only quantum mechanical problem we really know to solve, at least in class on the board, is the harmonic oscillator. The problem is that the Davis-Cummings model, or maybe say 2 coupled harmonic oscillators. Okay, that's something we can do. The problem is that here you don't have an harmonic oscillator. You have one harmonic oscillator, which is fine, but the other one is a spin, and the spin is very nonlinear. Why is it nonlinear? Because say the equation of motion, actually that's something we have already seen here. The equation of motion are nonlinear, right? You start with sigma minus and you end up with something like sigma z plus sigma minus. And the more you go on, the more it never ends. So there are more and more terms that need to be taken into account. So the spin is really a nonlinear system. That's also related to the fact that an harmonic oscillator, you can be as wide as you wish, right? You can excite it as much as you wish. The spin, the beginning it's fine, you can excite it, but then there is an upper top. Right? You cannot excite it more than n. So the Holstein-Primakov approximation basically is a way to transform a spin into a boson. Okay, that's the idea. We transform a spin approximately into a boson. How we do that? So first of all, we introduce an exact mapping between spin and boson, and then we do an approximation. So the exact mapping is the following. The exact mapping does the following. So let's say that sigma z is going to be minus n over 2 plus b dagger b. What does it mean? It means that you have now a boson that counts the level of the spin. So no boson means all the spin is down. Whenever I add one boson more and more and more, then it's like adding more and more bosons. Sorry, when I go up in the spin ladder, it's like adding more and more bosons. Okay, so these spin ladder operators are substituted by bosonic operator. This is fine. I mean, I can always do that. But what I also need is to preserve the commutation relation. And this is done by defining a sigma plus operator as follows. So roughly speaking, sigma plus is b dagger, right? What does it mean to go up in the spin? It means to add a boson. But to satisfy the commutation relation, this needs to multiply it by some ugly factor, which is n minus 2 b dagger b. Okay, this term basically causes that if you are, let's say, already in the n over 2 state, so if you have already, no, wait a second. No, this is incorrect. It should be n minus b dagger b. So this factor, what it does for you, it's a factor that if you already reached the state with n boson, the state with n boson is like the spin pointing up. you start from n over 2, and then you go up and up and up and up and up and up until you have added n photons, bosons. When you have added n bosons, you haven't gone from the minus n over 2 to the plus n over 2. And so then you cannot go up anymore. So you see that this term will tell you that if you try to apply S plus to a state that has already n over 2, that are already n bosons, that you stop. You cannot go up anymore. It's not only that, it really satisfies the commutation relation. So I leave it as a homework to show, for instance, that say sigma z commutator sigma plus equals to sigma plus. So just the canonical commutation relations of the spins. And you can check that these are exactly, this is not an approximation, this is an exact mapping. So these commutation relations are exactly satisfied. Okay. And this is known as the Holstein-Primakov transformation, which, okay, now where that comes the approximation? The approximation goes as follows. We say, well, let's assume that we are interested mostly in the ground state. In the ground state, well, at least in the normal phase, before you cross the phase transition, in the ground state, there are basically no spin. I mean, all the spins point down. So there are basically no Holstein-Primakov bosons. Okay, so what we do, we approximate this as square root of n times b Dicke. So this works only if b Dicke b is much smaller than n. Okay, meaning if the spins are mostly polarized down.
Emmanuel?
Yes.
Is it necessary to change the location of the square root and the b?
Yes,
No,
because b and b Dicke do not commute. So it's important. I mean, whether the square root is on the right or on the left is not. I mean, it's,
no, I was referring to after the approximation. But
no. This is just a number. I mean, the number you can put it on the right. Okay. So once you do that, you can. What happens to the Davis-Cummings model? So Davis-Cummings will become omega 0 Dicke rate. Here nothing happens. Plus omega z b Dicke b. Actually, let me see. So basically, yes. So right. So I just have satisfied sigma z with minus n over 2 plus b Dicke b. So there was a constant, which I don't care, just an energy shift, plus this term omega z b Dicke b plus g times a. Actually, g square root of n times a b Dicke plus a Dicke b. Okay. So this is now a coupled harmonic oscillator. And that's something that we can already deal with. Right? Is it clear this term where it comes from? But the term really comes from here, right? You had this S plus, which is now B Dicke, and S minus, which is now B. Okay, good. So let me comment. Let me make one comment. You see that there is this G square root of n terms coming in. This is the same as before. When we studied the dynamics at the beginning, I've shown you that the effective coupling is G over square root of n. Sometimes this is called the G tilde. We use G tilde to define G square root of n. And actually, in some cases, this is actually G itself. So this is also termed G. So one needs to be careful. In other words, sometimes you actually put in the Hamiltonian itself, you put the G over square root of n. So instead of using G, you use G tilde, which is G over square root of n. Okay, so you need to be careful whether there is a square root of n in the Hamiltonian or not. In this case, in this lecture, I'm assuming that there is no square root of n in the Hamiltonian itself. And so the effective coupling is actually G times square root of n. But sometimes people refer to G times square root of n as G. So be careful about whether there is square root of n or not. Okay, so this Hamiltonian, we can now write it in a quadratic form as follows. Something like, we can actually, let me do a dirty trick, which is to write it as A B Dicke times omega 0 G square root of n G omega Z A dagger B. So in principle, this should be like a 4 times 4 matrix, right? Because you have A dagger, B dagger. But I can simplify it if I put on the left A and B dagger and put on the right A dagger B, up to a constant, I get exactly the same Hamiltonian. So you see that this is A dagger A, this is actually B, so this is A dagger, but A dagger is up to a constant A dagger A, and this is B dagger B, so it's fine. And this is a B dagger, this is actually, sorry, A B dagger, this term is A, one second. No, actually it should be, no, it should be this way. I think I've done something wrong here. Yes, okay, sorry. Okay, now it's better. Okay, good. So this is basically A B dagger, and this is B A dagger. Okay, that's fine. So that's actually fine. There is no tricky with this thing. Just very, very simple. Okay. So what you need now to do is basically a rotation in AB space. That's what we need to do, right? We have now, we now want to define an operator, say an operator, let's call it alpha, which is some U, which is a some the operator alpha is going to be some U A plus V B. So you need to rotate in the AB space. Okay? Just a normal rotation. It's not a symplectic rotation. It's just a rotation between A and B. It's not between, say, A and A dagger. So you just need to rotate in order to diagonalize this Hamiltonian, just to rotate this 2 by 2 matrix. And so it means that the eigenstates are the eigenvalues of this matrix. Actually, we are actually really interested in the phase transition. So in the phase transition, in order to study the phase transition, what you need to have, so what is the phase transition? The phase transition occurs when the gap closes. What does it mean? It means that where there is an excitation that has zero energy. So the phase transition is like demanding that this, let's call this matrix M, that M has an eigenstate that is zero. But what does it mean to have, sorry, an eigenvalue that is zero? What does it mean that the eigenvalue is zero? It means that the determinant of the matrix is zero, right? You remember that the determinant of a matrix is the product of the eigenvalues. So a condition that is sufficient and necessary for having an excited state of zero energy is to require the determinant of the matrix is zero. I mean, you can also, if you want, you can also solve it, find the eigenvalues of this 2 by 2 matrix and demand one of them to be zero. But I'm just saying we can actually skip that step and we can simply demand that the determinant of the matrix is zero. Then we know that there is an eigenvalue that is zero, meaning that one of the excitation, that there is an excitation state that costs no energy. We can excite the system at no energy. Okay, that's precisely when the gap closes. That's precisely the place of the phase transition. And so this means, in this case, it means that omega 0 omega z equals to G square root of n. Sorry, there is also square root of n here. Okay, so G squared over n, G squared times n. Okay, so in other words, G squared equals to omega 0 omega z divided by n. And this is actually this is the correct. So there is with respect to the qualitative description that I gave you before, there is a square root of n. There is a square root of n difference. And actually, if you go back to the description that I gave you before and take into account really the matrix elements. So here in this case, I have just studied the transition between these two states, but I didn't take into account the matrix elements. And if I took the matrix elements into account, I would have found exactly the square root of n. This comes because of, remember when you apply the spin operator has this square root term that comes about. And so this is exactly the square root of n that you would have obtained. Okay, also in that case, it was just on resonance. So in that case, I assumed that omega 0 was equal to omega z. So that's why in that case, I had just g equals to omega 0. There are two differences. First of all, omega 0 needs not to be equal to omega z. And then n, also there is a factor of n that needs to take into account. Now, what you will do in the homework, you will use the same approach, but for the Dicke model. So the Dicke model is the Cummings model with counter-rotating terms. Okay, it is actually very, very similar. These are also you will also obtain two harmonic oscillators. The difference is going to be that in addition, you will also have terms like plus A dagger, B dagger, plus AB. Okay, this is the only difference in the homework. And then you need to do a little bit more of to work a little bit harder because it's not a 2x2 matrix. But you can write it as the product of 2x2 matrices, so it's still doable. Or you can write it as a 4x4 matrix and diagonalize it. It's also not a big deal. Okay, good. So this is the ground state phase transition of the Hepler and Lieb of the Dicke model, Cummings model of the Dicke model. Now, I would like now to discuss the experimental realization of this phase transition, of this quantum phase transition. And so actually, the first important contribution towards the experimental realization was actually something called the Nogo Theorem. The Nogo Theorem basically states that, before explaining Nogo Theorem, let me explain you what would be the simplest realization of such a model. Would be, as we explained, just two-level systems, put them in a cavity, and then, well, you know that the coupling, G is the coupling between the spin and the cavity. Usually it's relatively small, but you have this n factor. So even if, let's say, omega 0 and omega z are very large, okay, let's say they could be even optical. Well, maybe if they are optical frequencies, it's sort of a problem. But let's say that omega 0, omega z could be relatively large, you know, in the scale of, say, even electron volts. G squared needs to be however higher than omega 0 omega z divided by n. So in principle, if n is large enough, then you should be able to reach this phase transition. The problem, so the Nogo theorem says that even if you do reach this limit, you will still not have a phase transition, and the reason is that when you really study from the microscopic model, you derive from a microscopic model of an interaction between light and matter, you will obtain additional terms. These are related to the A square terms. So if you remember from electrodynamics, you know, in the electrodynamics, there is the coupling between atoms and between matter and light is something like P minus A squared, right? Remember this? You remember this this expression E over C times A. So this is the way that you couple an electromagnetic field with matter, and there are terms that are proportional to the electromagnetic field. So these are these terms. These terms in the Cummings model, these are terms that there are linear terms, okay? Terms that can create a photon like this. So these terms actually derive from the A term, the linear term, but there is also an A square term. And the A square term basically modifies the cavity. So if you want, the electromagnetic field is modified by the interaction. And the problem is that the two couplings are the same. So when you make stronger the coupling between the spin and the cavity, you're actually more modifying the cavity. And the Nogo theorem tells that the two effects cancel in such a way that you will never be able to reach the superradiant phase transition. Because in a sense, you are increasing G, so you're increasing the coupling between the cavity and the spin, but you're also making your cavity stiffer. The energy of the cavity is stiffer. And so eventually you are not able to cross the phase transition. Now, there are arguments that it is debated whether this theorem really applies or not. Some people say that for sure, no one was able to observe the phase transition. And some people say, oh, that's because of the Nogo theorem. But others say, no, actually, this is just because no one was able to reach such a huge coupling. Because think of omega 0 being an optical frequency, and G, it's okay, the interaction between spin and the cavity, usually say in the kilohertz, maybe megahertz values. So you would need a lot of atoms. And as we recall, all these atoms need to be in the same place, or maybe at the distance lambda. But then how do you keep them exactly at distance lambda? So people claim that maybe there are really technical problems in realizing, just the people who were not able to reach such a strong enough coupling in order to observe the phase transition. So there are arguments whether is it really because just a generic theorem, or maybe just because one was not able to reach such a huge coupling. So the reason I'm mentioning this whole problem, and I got interested in this whole problem, is that in 2010 there was an experiment which we are going to see in a moment, in 2010 by the Tillman-Esslinger group, where they realized the phase transition. So the way that they realized the phase transition was to use a different coupling that is not the dipole coupling. In other words, the ground state and excited state are not going to be the ground state and excited state of a two-level system. It's not just an atom that has a ground state and excited state. And in a way, if you want, in a sense, they reduced a lot omega z. Okay, so omega z is now, there are going to be two levels that are quite about the same energy. I'm going to discuss in a moment what are these two, what is this energy scale. So they reduced a lot omega z, and also they work in a rotating frame. And so this omega z is now going, instead to be the frequency of the cavity, is going to be the detuning between a driving field and the cavity. And the detuning can be as small as wish. Okay, so the experiment is done in a rotating frame. Okay, so it's a rotating frame. So that actually omega 0 is just a detuning. And omega z, we're going to discuss it, is going to be related to it's going to be related to the recoil energy of the atom. So it's going to be much smaller. Okay, so combining these two ingredients, they were able to reach the phase transition. Now, people say, and actually this is also correct, is that this experiment doesn't show that Nogo theorem does not apply, because the experiment was performed in a rotating frame. So the Nogo theorem applies to just a static coupling between the cavity and the atoms. Here we have a rotating frame, so it's a non-equilibrium problem. Maybe this is why they were able to observe the phase transition. So still the argument whether the Nogo theorem in the static case applies or not is still debated. But at least one was this experiment was able to realizing in a different way, okay, but in a different frame where the Nogo theorem does not apply, and when also you can reduce omega 0, omega z. So that's the state of the art. Okay, so let me show you now a microscopic derivation of the experiment. Okay, let me actually do the following. Let me take a technical break of 5 minutes, and then afterwards I will describe. I will briefly describe the experiment, how it is related to the Dicke model, and then I'm going to show you the experimental data itself, and then we will have a presentation by one of the students. So 5 minutes break, technical 5 minutes break, and we are back. Okay, we are back to business. Okay, I'm waiting 1 more minute. I mean, if you can turn on your camera, then I know that you are back from the technical break. Okay, very good. Welcome back. So, experiment. So I'm going now to describe briefly the experiment, and we are going to see the data in a moment. So the experiment, as we mentioned, is an experiment which you have too many two-level systems that are inside the cavity. Okay, and we are trying to realize the Dicke phase transition, Dicke model. So how is this done? So this is done as follows. So basically what you do, you pump some energy transversal to the cavity. Okay, so in all the atoms, let's assume that they are sort of in a very thin layer, even in one dimension, like a cigar shape, in a very thin layer. And from the side, you pump energy into the cavity. Now, if there were no atoms, this light would just cross the cavity and go away. That's it. Actually, in practice, what they do in the experiment, they put here a mirror. So eventually, this light is reflected back, and there is a standing wave, but that's not the key ingredient. So for simplicity, let's assume that the light would just go away. Now, what do the atom do? The atom scatters light into the cavity. And actually, let me describe this experiment in what I refer to as the strong coupling limit. What does it mean? So let's assume that the atoms scatter so much light into the cavity such that a standing wave is created in the cavity. Okay, so let me use a different color. So let's say in orange, what we have is a standing wave of the light inside the cavity. Now, as we have studied earlier on, the force that the lattice applies on the atom depends on the intensity square, meaning that the distance between two minima of the potential is actually lambda over 2, right? Remember that when you have a standing wave, so basically, let me just draw it here in this orange line. So you have a standing wave. So this is at some time t, and this is in another time t. So there are nodes, right? And antinodes, again, depending on whether this blue detuned or red detuned, the atoms are either attracted to the nodes or to the antinodes. Let's assume, for instance, that they are attracted to the nodes. The important part is that the distance between the nodes is actually lambda over 2. Okay? This is just a basic standing wave. So the potential, let's assume, is so strong that all the atoms either all the atoms fall only on the nodes. Now, the nodes, however, are different, and so how can we describe this such a situation? So what happens here is that whenever a photon from the pump comes into the atoms, it is scattered into the cavity. Now, the important part is that initially, the phase of the light that comes in is the same for all the atoms, right? At a given time, let's say at a fixed time, then all the atoms experience phase 0. After half a period, phase pi, and so on. Now, because the atoms are if the two atoms are differ by lambda over 2, the phase by which the light is scattered into the cavity will be different, will be either 0 or pi. So let's assume that all the atoms feel from the pump phase 0. Now, when they scatter light into the cavity, depending on the position of the atoms, this translates into either a phase of 0 or a phase of pi, because the distance between the atoms is lambda over 2. So if you want, in the vertical direction, they are all at the same place. So in the vertical direction, from the pump, they all feel exactly the same phase. However, when they scatter in the cavity, so in the horizontal direction, the distance is lambda over 2. So in the horizontal direction, there is a phase difference of pi. And that's why the Hamiltonian that describes such a situation is something like A, say G, which is the scattering, times A dagger A, times sigma Z I, where sigma Z I, of course, there is always the emission conjugate. What is sigma Z I? So let's say that sigma Z plus 1/2 is here, and sigma Z equals to minus 1/2 is 0. So let's take all the nodes, and then the nodes that are even, we call them plus, and the nodes that are odd, we call them minus. And what I mentioned here is that this is a photon in the cavity. Okay, this is a cavity photon. And the cavity photon acquires a phase depending on the position of the atom. If all the atoms are in the even, if all the atoms are in the even sides, then the photons are scattered all with positive phase. And if an atom is in the odd side, the photon is scattered in the with a minus phase. So if two atoms sit in, say, near neighboring sides, actually they destructively interfere, because in a standing wave, the phase there is a phase difference of pi between these two positions. So if I emit light with the same phase here and here, actually they destructively interfere in the vertical direction. Maybe it would have been easier if I had put my my atoms in the antinodes. It would have been easier, but it's exactly the same. It would have been easier to see. Okay, let's put my atoms here in the antinodes. Okay, then in the antinodes you see more easily that indeed there is a phase difference between the two. This is a minus 1/2, right? Because when the atoms, these atom and these atoms emit light at the opposite phase. So if there were an atom at site 1 and an atom at site -1, they would emit light in the vertical direction with exactly the opposite phase, and it would be destructive interfere. I mean, also in the antinodes I think it's easier. Yeah, it's easier to see when you put them in the nodes. Okay, so that's why what I described here. So this is basically the scattering from the pump. Scattering from the pump. The scattering from the pump creates a photon in the cavity with a phase that depends on the position of the spin. So this is why there is a connection between the spins and the photons. Now, what other terms we have? We have an omega 0 A dagger A. Okay, this is just the detuning between the cavity and the pump. Okay, because we are actually working in the frame of the pump. Okay, we are working in a rotating frame that rotates at the frequency of the pump. And so if the cavity is detuned, there is a finite omega 0. Plus, there is a quantum mechanical term. What is the quantum mechanical term? The quantum mechanical term describes the process of atoms hopping from one side to the other. Right? As we mentioned, there is like an optical lattice. So the standing wave creates an optical lattice, and the atoms can quantum mechanically hop from one side to the other. And so in the hopping would be some J, say hopping term, times sigma xi. Why sigma x? Because sigma x flips from up to down, right? This is from down to up. And indeed, when you jump from even to odd sides, this is equivalent to having these spin operators that flip from positive to negative. If you assume that you are hopping only between nearest neighbors, so you hop from, say, an even side to an odd side, and therefore sigma z goes from plus to minus. And the operator that brings sigma z from plus to minus is sigma x. And now, when you look at this Hamiltonian, this is actually this is exactly the Dicke Hamiltonian. Dicke Hamiltonian. Of course, we have swapped the roles of x and z, but who cares? If you go back to the Dicke Hamiltonian, we had here sigma x and here sigma z. But I mean, this is completely arbitrary. So if you want just to call this sigma z, sigma x, this sigma z is exactly the same. So the statement is that this is this Hamiltonian. This experiment realizes the Dicke Hamiltonian. Okay, so while you think, if you have questions, I'm going to switch to the experiment itself. I'm going to show you some data from the experiment. Okay. Well, okay, so this is the experiment itself from 2010. So you can see here how this is the same drawing that I've shown you before. So there is a gas of atoms, a gas of ultra-cold atoms, and there is a pump from the side. Also this is important. This is a detector. So the question is, how do you distinguish between the superradiant and the normal phase? We're going to see that essentially in the superradiant phase, there are a lot of photons in the cavity. Why? Because all the atoms constructively interfere. So it behaves a little bit like a laser. So it creates a lot of light into the cavity because there is constructive interference between the light that is scattered from the atoms in the cavity. And here, this is what is mentioned. So in the normal phase, there is destructive interference. So there is basically no light into the cavity. And in the superradiant phase, the atoms, first of all, the atoms form this lattice. That's the lattice that I was telling you before. And the distance between the atoms is actually lambda. So they say all the atoms occupy either the odd sides or the even sides. Okay? And there is light that is transmitted out of the cavity. Now, by the way, this is exactly a phase transition. Phase transitions that breaks symmetry. In this case, the symmetry is the symmetry between even sides and odd sides. So at the beginning, the atoms are equally distributed between even sides and odd sides. In the superradiant phase, they decide sort of a collective decision of where it is better. So they either all or most of them or a majority of them sit in even sides, so that the light into the cavity will have a given phase, say phase plus, or they also sit in the even sides, and then the cavity in the field will have a minus phase. So actually, this was not shown in this first paper, but there is a follow-up paper where they show that indeed, when they cross the phase transition, sometimes they end up in phase plus and sometimes in phase minus. So in other words, sometimes the atoms are in the even sides and sometimes in the odd sides. Okay. So the way that they derive the Dicke model for this experiment is a different way, and you can read that in the paper itself. So it's interesting because you end up with the same model. It's the same experiment, the same model, but they use a different derivation. So in my derivation, I assume that there was already a lattice. Okay, so I call it a strong coupling approach. Instead, what they do instead, they start with no lattice at all. And they assume that all the atoms are found in the BC state. So all the atoms are found in the zero momentum state, the BC state. Now, what does the potential do for you? The scattering potential basically moves the atom, scatters the atom by momentum K. Okay, that's basically, actually, what you really actually do, you absorb a photon from the pump, and so look it by here. So you are starting in zero momentum, then you absorb a photon from the pump, so your momentum goes up. Say, let's say that the light comes from above. So if the light comes from above, then when you absorb a photon, your momentum goes down, because you know that photons has a momentum h bar k. So you absorb a momentum photon h bar k, but then you re-emit the photon into the cavity. And when you re-emit the photon into the cavity, you are actually moving in the vertical direction, right? Because to emit a photon in the cavity, you need to put a momentum in the vertical direction. So eventually, you end up from this state to this state here. Okay, so actually, the 0 and 1 state in this description, the zero state is a BC state, so zero momentum state, and the up state is actually superposition of all these momenta. So because you can do all these processes by the same intensity. So you are either at zero momentum or at finite momentum. Okay, and initially you're mostly in the zero momentum. Then after you cross the phase transition, there is actually a finite number of atoms that will be found in the finite momentum transition. So this is a different description. There is also in the paper also the description of even size and odd size that I gave you. So they sort of go in both directions. Both directions are eventually you end up with the same model, but it's just a different starting point. This is how the experiment looked like. So what we are showing here is this is basically the expansion of the atoms. So you take your atoms and you expand them. And what you see is that initially they were in the BC state, so all at zero momentum, while after some time, so the horizontal axis is the intensity of the pump. So at no pump, there is just a BC. When you increase the pump going through the right, you see that after some point, the BC transforms into actually something that has a finite momentum Fourier transform. But what is the finite momentum Fourier transform? It means that basically the atoms are now in a lattice, right? That there is you can think of these as like delta functions of the density. So it means that in a sense, the density now, instead of being constant, is now oscillating in space. So these finite momentum peaks mean that the atoms are now formed a lattice, and you can see here as a function of time. So function of time means basically what they do. They start with zero pump intensity and increase the intensity of the pump as a function of time until they cross the transition. So you see this sudden jump here. This is the place where the transition occurs. What is shown here is the mean photon number. So you can either look at the atoms and you see that the atoms go from the BC to this potential, to this odd even potential, or you can look at the photons actually out of the cavity, which is a proxy to the number of photons in the cavity. You see that the number of photons in the cavity is very, very small, until it suddenly grows. And so this is really the phase transition, this quantum phase transition occurring from a zero photon state. So, this is sort of no photon state to a finite photon state. That's the phase transition. Actually, what happens as a function of time is that, in fact, as a function of time, the photon then drops. So initially, the number of photons goes up, but then it starts going down and down. And this is essentially, you can think of it as the photons moving away from this simple two-level system. So in the two-level system, we assume that there are only two possible states, but as time goes on, the number of the atoms can occupy also other states. And so these other states make your model not relevant anymore. It's a bit like as if another way to think about it is that the total spin now starts decreasing. So at the beginning, there is a lot of emission, but then the total spin decreases because you sort of lose atoms. They don't go away, but they go away from this simple two-level system. And then you end up again with no photons. So it's not really a steady state. It's just a transient. But the transient, as you can see, there is a sharp transition in the transient. That's enough to sort of call it a phase transition. And you can see here, this is a standard phase transition plot. So in the X and Y axis, you have, in the X axis, you have this omega 0, okay? In the Y axis, you have the lattice depth. So the lattice depth is something like proportional to omega Z. Yes. What you should see here, let me see. So you see that for a fixed value of G, let's say if there is a fixed value of G, then when omega Z, yes. Okay. So, okay. Yeah. The truth is, I don't remember. So how does it work? Okay, I don't remember. This is so this dashed line is basically meant to mimic this phase transition. Now I forgot
Manuel?
why you see. Yes.
What is the x-axis? I can only see the numbers, but not what it
It's
represents.
this is basically you see the
On the
x-axis.
bottom.
This is an x-axis. It pumps lattice depth. So this is basically the intensity of this is the intensity of the pump. Okay, thanks. Okay, excellent. Thanks. Very good. So what you see here is basically G is proportional to the intensity of the pump. Okay, the intensity of the pump is what creates the coupling between the spins and remember that what was G was the scattering of photons from the pump into the cavity. So what you are doing by increasing the pump lattice depth is just what you see here is okay, I apologize for having cut down the units, but this is the strength of the pump. Okay, this is just the intensity of the pump. So the more so you increase omega G squared is proportional to the intensity of the pump, and what you see is that there is sort of a linear dependence between the critical. So basically, you go in the horizontal direction. So you start with zero pump, you increase the pump, increase until you see a jump. And this jump means that you have crossed the phase transition. Now you vary the detuning. Okay, so you vary omega z. Remember, omega z was the detuning between the pump and the cavity. And then you repeat the experiment. You start with zero pump until you cross the phase transition, and so on and so forth. And you see that there is a linear dependence between omega 0 and G0, G squared critical. This is the critical value of the intensity of the laser. So the larger the tuning is, the more you need to put in pump in order to cross the phase transition. Yes, okay, this is what is shown here. That's it. Yeah. So yeah, so if you have questions. No, okay. So then I think we have a presentation by Guy. So next week, I think Mor is going to present like an extension that we did on this model. So we basically consider the model that interpolates between the Davis Cummings and the Dicke model. It turns out that in this lecture, I'm presenting something at a very basic level. So I presented as if the Davis Cummings model and the Dicke model are basically almost the same. It's almost actually the same phase transition. But this is not actually the case. So the Davis Cummings model, as we have seen, very much reminds us of the lasing transition, while the Dicke model, if you think about it, if you try to derive the equation of motion, you will see that it actually reminds much more of these parametric resonances. So the distinction that we had between parametric resonance and lasing is actually going to apply also here between the Davis Cummings model and the Dicke model. The two models actually display, the reason is that they have a different symmetry. Maybe More will comment on that more. So, maybe I will add a little bit more on the distinction between Davis Cummings and Dicke model after More's presentation. Yeah, but that's all for now. Okay, so Guy, you're welcome to show your presentation.
Yes. So I need to share my screen.
Yeah, I think you are allowed.
Let's see. Can anybody? Do you see this?
Yes.
Right. Hold on. Right. Okay. So the paper that I'm presenting here is from 2016 by a guy named Jeff Steinhauer. He's from Technion, actually. A paper from 2016 about the observation of quantum Hawking radiation and its entanglement in an analog black hole, which sounds very mysterious to me. And it's not really my field of study, but I think it's an interesting topic, and it's very much a quantum simulation. So I'm gonna talk about some theoretical background, but not too much into it because you know, we don't really know general relativity that well. So I'm gonna try to work around it. So first of all, I'm going to talk about black holes. So we all know that a black hole is when a star is sufficiently massive and it exhausts its nuclear fuel. It undergoes a huge explosion, which is called a supernova, and it's, so to speak, it collapses right out of existence. So this picture in the right is from the Hubble telescope of remnants of a supernova. And the picture from the left is very, very famous. It's like the first image of a black hole. And it is said that any matter or radiation inside a certain sphere of the black hole cannot possibly exit it. So it falls out of our causal connection. So without dwelling too much into the theory of general relativity, I found that you could basically explain this even in a classical Newtonian way. And people have done it in the 18th century, Mitchell and Laplace. So we're all familiar with the concept of escape velocity. And here we can see here, this is just a regular formula for escape velocity. So Mitchell and Laplace thought, what if we take this speed velocity to be the speed of light? And at the time, some physicists thought of light as particles. So if we take v to be speed of light, we can have some exotic behavior where even a light-like particle cannot possibly escape a star that is massively enough from a certain radius. So this radius is called the Schwarzschild radius. And surprisingly enough, even this very, very simplistic classical treatment, this is the actual relativistic results by Schwarzschild himself in the beginning of the 20th century. So it's quite nice to see this. So after we discussed about this, we can talk about the Hawking radiation. So basically, within the Schwarzschild radius, any light cannot possibly get out of the Schwarzschild of the radius, and it's impossible to be observed. So in 1975, I think, Hawking made a paper that proved that there's an effective radiation, because he asked what happens to the vacuum fluctuation very, very close to the event horizon. And he proved that within very close to the event horizon, where particles and antiparticles are always created and annihilated, he schemed a process in which a photon exits, enters the event horizon and therefore lost for any observation, and another photon is still out there, because outside the Schwarzschild radius, there's nothing special about a black hole. It's just a gravity field. So what happens is one photon is trapped inside and one photon escapes. And it behaves like a thermodynamic distribution, like a black body radiation, effectively. So this is the formula he achieved, which is it's a very nice formula because it has like all the constants of all the major constants of physics. It has h bar and it has the speed of light, It has a G from gravity, the Boltzmann constant. So it's very nice. And it's also a black body radiation, which means it behaves like in a somewhat of a equilibrium with the environment, and it's also random. It's a random distribution. So some paradox arise from this kind of observation. First of all, I'm going to say that the reason that you can't possibly detect this radiation is because if you plug in the regular mass of most black holes, you see that this temperature is about is less than a microkelvin, so it's undetectable for us now. But even if we get smaller and smaller black holes, we have a much hotter black hole, which is maybe be able to be detected. So some people propose to maybe it will be able someday to even create one in the Large Hadron Collider, or maybe some smaller black holes could be found in an earlier universe. But so far, there's no evidence of real evidence of this radiation. And it leads to many paradoxes actually, but one of them is the information paradox, which basically says that since it's a black body radiation, it doesn't carry the original information of the photons entering. And even more interesting, it leads to the fact that the black hole eventually evaporates because it loses energy all the time. So photons entering the black hole is considered to have negative energy, which at the end evaporates the black hole after like 10 to the power of 17 years. That's the fate of any black hole. So there are many ways that people are proposing to solve this information paradox, and it involves a concept like firewall and software theorem, which I'm not really going to discuss here. So what's interesting about this is that people have proposed a way to simulate black holes. First of all, Unruh made an observation in '81 about some sort of analog black holes in water, which is a classical system. But instead of sound, instead of a light, he thought of sound. Like phonons can be considered as photons in this example. But people are now thinking of many other ways to try to emulate a black hole with superfluid helium-3, with electromagnetic waveguides, ultra-cold fermions, a ring of drat-ions, and nonlinear fiber optics. But I'm going to discuss the only one that actually has fruition in the experimental world. So, stuck for some reason.
Guy, do you have an example for? You know what? I'll ask at the end. So
yeah, I'm going to show. Yeah, so I'm going to show like the very, very basic idea of how an analog black hole works. This is actually from Unruh's paper, one of his papers. It's very ridiculous sketch, but it has you can understand it quite well from this. So you have a fish that's swimming here, and a sound wave can propagate freely in this space, but in the waterfall, sound wave cannot possibly reach the other side. So this is like they're trapped in this area. So any simulation of analog black holes has some border that acts like a event horizon, where where the phonons cannot possibly escape. And in this paper from 2016, what they did here is they take a Bose-Einstein condensation, and they have two regions. One has a subsonic flow, and the other has a supersonic flow. So any phonons trying to come from the inside outside are carried by the supersonic flow, and they cannot possibly reach back to the horizon. So this is effectively our universe, and this is the inside the black hole, effectively. And we can see they use Bose-Einstein condensation of rubidium, I think. And this graph is basically the distribution of atoms. And here is, well, they moved it all the time to make it work. So this is irrelevant right now. This is the position of this step potential. They created a potential, which is effectively like the waterfall we saw earlier. And it moves all the time. So this is how it moves. They've done several experiments with it. They try to make an oscillating black hole, which is this is another phenomenon, but I'm not going to speak about this one. So basically, what we're looking at, what we're looking to find, is a spontaneous. It's not spontaneous. It's like a vacuum fluctuation that's emanate from this horizon. So basically, we're looking to find some correlation, some particle-antiparticle pair that's created both in the inside of the black hole and the outside. The nice thing about these experiments is that we get to have a peak inside the black hole, which is obviously impossible in the real world. So what they did in the experiment is they were looking for a vacuum fluctuation. They put the condensate in a vacuum, and they measured some correlation of phonons between any point x and x prime. That's basically, so this is the correlation function. It's not very important right now, but what they found is a very strong correlation. Here is the x and x prime. Graph A is the relevant one here. It has a very strong correlation between them. So basically it means that they found a particle-antiparticle pair that acts exactly like the Hawking radiation. Tzachi, you wanted to ask something, or maybe just okay.
I did, but I could wait to the end of your presentation.
Okay. Yeah. Okay. So this is a bit more about the experimental stuff they use. It's quite complicated, but what's important here is that they use some Gaussian beam laser to make this step potential. So basically, there is a strong repulsion. Yeah, there's this like effectively a gravity going from the outside to the inside, and this imaging is only for being able to detect anything, and they also use a magnetic field to make everything resist gravity. I'm not going to go too much to these details, but they basically used lasers to create a potential, and they moved the laser around, and they measured everything in the laser frame. So basically, this entire thing moved all the time, and this step potential moved to the left, and that's how they created a flow of Bose-Einstein condensation, because effectively the Bose-Einstein condensation moves from left to right in relative to the laser. So that's basically it for now. Well, I don't think I showed the, yeah, I showed the result. So that's basically it for now. And the correlation found is actually this pretty much the first ever realization of any concept that's revolve quantum gravity. So maybe people are going to use this later to confirm some other pieces of the puzzle that's quantum gravity, because it's a very mysterious and unfamiliar territory of physics. And that's it for now. If you want to ask a question, feel free.
Well, Guy, thanks a lot. Yes, so there was a question waiting.
Yes, I had a question. It's about nonlinear optic fibers. Do you know what is the analog?
Yeah,
Yes.
I assume that every experiment is kind of in a similar fashion. So I assume they use the fiber that is very, very strongly nonlinear. That I don't know. I guess speed of light is. Well, I don't want to be too. I can show you the papers, but I haven't read them yet. So maybe I'll show them later for you.
Okay, even a reference will be grateful. Great. Sorry.
Yeah, I'll send it to you. Okay, anything else? Okay.
Okay, thanks, Guy. This was very, very nice, and I think it's really a nice example. You know, in my course, I have chosen examples that are very simple. You know, models that are very, very simple, basically coupled harmonic oscillators. And I really appreciate the fact that you chose something else, which is much more complicated. You know, some quantum gravity, nonlinear differential equations, so that we can taste the fact that it's not everything is just harmonic oscillators. So that's very nice. Yeah, okay, so thank you, and we'll meet next week. We'll see, hopefully frontally, if the situation improves, or on Zoom. I have internet in my secured room, so everything is fine. Okay, then take care. I hope you are all fine, especially for those of you who live in the south. And I see you soon.
Thank you.